thank you to the organizers for giving me the opportunity to present some of my research. Yeah, this is joint work in progress with Jeong-Seop Kim. Okay, yeah, so at every conference, there is this guy who gives a talk about something that is very loosely related to the subject of the conference, and I'm going to be this guy. Okay, yeah, so let me start. So and also I'm too stubborn to use slides. Two notions, two fundamental notions that will be important for this talk. So if I have Y, normal, projective to factorial variety Y, sorry, this is Y. Normal Q, projective Q factorial, we say it is a Mori Dream Space if the following three conditions hold. So first, that Picard group of Y tensored by Q is N1Q. So this essentially says that the Picard group is finitely generated. Second condition is that the Neff cone is rational polyhedral generated by semi-ample classes. Yeah, so the Neff, okay, I should make it write slightly bigger. Yeah, it will be fine. Okay. Yeah, so the Neff cone is rational polyhedral generated by semi-ample classes. So essentially, the Neff cone, the semi-ample cone coincide. And the third condition is that there are finitely many maps more irrational modifications from our variety Y, from Yi, such that the movable cone of Y is precisely the sum of the pullbacks of movable cones, the Neff cones of this Yi. So yeah, I have like some small birational modifications, and I get my movable cone. I have some Mori chamber decomposition on the movable cone that comes from this small birational modification. There are finitely many of them. So this definition, it was introduced by Hu and Kiel, some paper that is called Mori Dream Spaces and GIP. This is quite, I mean, this notion is good and bad. It's good because it gives you some very nice properties of this variety. This is like, these varieties, they are called Mori Dream because they are perfect for running MMP. Everything works fine. I do not run in any troubles with MMP. I can run MMP with respect to any divisor. It is bad because, I mean, it's not easy to say that something is a Mori Dream space. It does not behaves well in families, and yeah, weird notion. And okay, so the second definition, I promised two definitions, so I will do two definitions. Only two, I guess. So a Cox ring. So assumption as before. Plus, just for to make the definition easier, I assume that the Picard group of my variety Y, so remember like a normal projective, is 3 abelian with K generators. I can have torsion in the Picard group and I can define Cox ring still, but I want to do the easy things because I only need this easy definition. So let as peak V1. Okay, so these are some wildcards here, doesn't matter because divisors such that they generate, I mean, when I project them onto the picker, okay, such that O y of di generate picker group of y. Yes, then I define the Cox ring to be like the total section ring. So I have sections of, let's say, all possible line bundles on Y. So two definitions. What is the relation? The relation was given in this paper of Hu and Kim. And they say that Y is a Mori Dream space if and only if Cox Y is finitely generated. Okay, so this is like some toric condition that ensures that something is a Mori Dream space. So let me give some examples for these two related notions. So the first example, like the most important, and this is due to himself, that any toric variety by a fan, so a normal toric variety, has Cox Y equal to precisely the polynomial ring in some number of variables, and these variables Ti correspond bijectively to rays of fan. Yes, so you have a toric variety, you have a fan, you look at the fan, you have number of rays. I just put the polynomial ring in as many coordinates. This is my Cox ring, and this is like if and only if. So if something has a polynomial Cox ring, this is the toric variety. So let me do a sub-example of this example. So our guiding example would be X. So I will try to keep the notation that X is del Pezzo surface and Y is like just any variety. X6 is the del Pezzo surface of degree 6. So this is the last one. And I can draw the fan.
So just to make sure that the toric has to be smooth.
No.
Totally works. All work right. You use Vey divisors, you find it works the same. You know, you have to be a little careful with the definition, but it works.
Yes. I'm just simplifying stuff because I only need smooth, but you can define even if you have some torsion in the variety. Yes, so I have like six arrows that are 6 rays, and I can like name them somehow. X1, X2, X3, X12, X13, X23. So my Cox ring is the polynomial ring in those 6 variables. And that's nice. So this is like example 1. Example 2 that is also important to mention. So there is like this quite important paper. Birkar, Kashin, Hakon, McKernan, where among other things, they proved that Fanos and more generally log Fanos are Mori Dream spaces. So log Fano, is this like thing, does someone need explaining or it's fine? it's fine what is log Fano. Yes, so clearly every Fano is a log Fano, but weak Fanos are also log Fanos. Sometimes even I have some log Fanos such that the anti-canonical is not nef, but it needs to be big. I mean, the necessary condition for being log Fano is for the anti-canonical to be big.
You are thinking this as pairs, like X.
Yes. But the thing is that not always I can find this boundary divisor. And the necessary condition to be able to find such a boundary divisor is for the anti-canonical to be big. So this will come and be important for us maybe later. So yeah, log Fanos are Mori Dream Spaces. But determining the Cox ring is, we know that they have finite generated Cox ring, but if you want to really find them, it's not so easy. So I also need to mention that there is this earlier paper of Matirev and Popov, where they proved found the generators of Cox of XD. So any Pezzo surface, not just the toric ones. And okay, so I will tell you the answer, what they precisely proved. So for let's say degrees 5 to 2, the generators correspond bijectively to -1 curves on X. And for degree 1, I need to add 2 more generators somehow. So it's nice. But okay, this notion of being a Mori Dream space, it somehow cuts across all the, we have, I like to think about varieties that we have, Kawamata dimensions. So we have like Kawamata negative, 0, positive. But there are examples of Mori Dream spaces that are in all 3 classes. Some K3 surfaces, so some things that have trivial canonical are Mori Dream spaces, some general type things are Mori Dream spaces. But on the other hand, if I take even like, projective space and I blow it up enough times, I lose Mori Dream. It stops being a Mori Dream space. So this is like interesting notion, not so obvious. Okay, so this was like the 2 definitions that I need and some examples. So now let me give you the motivation. So 2 theorems. Motivation. Okay. So the first theorem that I want to mention is due to González-Hering, Payne and Süß, Hendrik-Süß. So they say that if I have this any toric variety, even smooth projective, and I take an equivariant vector bundle, then I cannot expect that if I take the projectivization of this bundle, that this is still a Mori Dream space. And in fact, I should expect otherwise, that this not a Mori Dream space in general. So this is like, very delicate notion. I took something that has the simplest possible Cox ring, and I just take some PR bundle over, and somehow I destroy this property. But there is another theorem, which is in fact slightly earlier. It was proved by Hausen and Hendrik-Süß. So they say that in the setting as before, so Y sigma is a smooth projective toric variety, the projectivization of the tangent bundle is a Mori Dream space. They even gave a precise algorithm how to compute the Cox ring generators relations. Yes. So let me continue our running example that of the Pezzo of degree 6. So
Let me ask if this has anything to do with the global sections or not, like what is the intuition?
Is this because of complexity 1T varieties, or is this?
yes, yes. So that proof of Jung and Hendrik, like they use the fact that there is a torus action, and in fact, I guess very often, if you want to determine the Cox ring, if there is some torus action, it's much easier. If you don't have anything, then it's difficult. Okay, so let me go. Okay, so we have like 6 rays, but we can like pair them because I have this ray and minus this ray. This is like one pair. Then I get the other ray, other pair of rays. So I have like that I denote by V, also ray and minus the ray, and I have the third pair. And yes, so we knew that Cox of x6 is C x1, x2, x3, x1, 2, 1, 2, x2, 3, 1, 3. Yes, and the Cox ring of projectivized tangent of x6 is the same thing as before. So we get Cox x6, and I add 3 variables that corresponds to these 3 pairs of rays. And there is a single relation that can also be okay. So like the generators, how to find generators in general? I just pair the rays like this. So I add 1 variable for each pair of rays that ray and minus ray is in the fan. If some ray is unpaired, then I just take it, this ray, and I add also a variable for this. And I have like 1 relation, so I have 3 additional, okay, so let's focus on generators. I won't be speaking about the relations at all. I just add 3 generators for each pair of rays. So the thing is, of course, what are these generators? They should correspond to some sections of some line bundles on the variety, on this projectivized tangent. So we'll come to this. But okay, so there is this motivation. So I have 2 theorems. Yes. So in general, line vector bundles, I cannot hope that nicely, but the tangent bundle for toric does behave nicely. So the question. Questions even. So the question is, what about why or why Mori space? Yes, so this is like a huge question. Let's take any other Mori Dream space that is not toric. Can I say that the projectivized tangent bundle is a Mori Dream space or not? So this question is like a probably, huge question, too complicated to answer, especially since this is a wide class in some sense. So this problem is, I believe, is of particular interest for fans. Not only because I like Fanos and Vanya likes Fanos, but I will later show you that maybe this really is a very interesting question for fans. Yes, so what for Fanos? And even simpler, so what for the Pezzo surface, the simplest Fanos? So today GP. Non-toric, of course, because we know how. Okay, I think I'm going very slow, but so I need, if I want to tell you what are the yi's and what we expect and what we are working towards proving, then I need to just recall you that del Pezzo surfaces be the structure of a conic bundle, and even like multiple structures of conic bundles. Yes, so I have some maps from XD to P1 such that the generic fiber is conic. There are no, there is some number of reducible fibers that consist of 2 minus 1 curves that are, yes, so we have precisely I minus D singular fibers. Okay, so from the general theory of everything, we know that if I have a vibration, then I have a relative tangent sequence. In this case, like this is vibration in some singular fiber, so it's not as nice, but I still have the relative tangent exact sequence. So I have the relative tangent bundle. I have the proper tangent bundle. And then I have the pullback of the tangent bundle from the base. But this is not everything. I mean, if this were a nice vibration without singular fiber, this would be it. But I have to twist it by the ideal of gamma, where gamma are the singular points of fibers. Yes, so in the case, let's say, of degree 5, where I have 3 singular fibers, this is ideal of 3 points. Degree 6, this is ideal of 2 points. Okay, so this is precisely what I care about. This is a very important short exact sequence for this problem, because recall that in the projectivized tangent, I mean, if I take any vector bundle and I projectivize it, then I simply have some line bundle whose sections essentially correspond to the sections of this vector bundle downstairs. So in my projectivized tangent P, T, X, D, I just add one line bundle, which is this relative O of 1, and the sections of this relative O of 1 correspond to the sections of the tangent bundle downstairs. And if I take like the twists of this O of 1, then this corresponds to taking the symmetric products of TXD, then I can twist it by something that I pulled from the base, and I can do this like upstairs, downstairs. Yes, so I often think about this tangent bundle, twisted tangent bundle, instead of thinking about this O of 1 on the projectivized thing. Okay? Yeah, so look at this short exact sequence. So I can twist this short exact sequence to get like O of XD, EXD, let's say minus T is relative. And so on, blah, blah, blah. But I have a section of this twisted tangent, right? Tangent twisted by the minus relative. So this is precisely, and for the del Pezzo of degree 6, the one that we studied above, right? I have 3 new variables. And this guy, X6, has 3 conic bundle structures. So these are precisely these variables that I see. So conic bundle gives me section, and this gives me some generator of the cost. So this is how it works for this toric guy. So the conjecture, this is not a theorem yet, but we are working very hard with Jeong-Seop to prove it, says that, okay, so conjecture says that PTXD is a Mori Dream Space. Moreover, Cox PTXD is equal to Cox of XD, and I add a bunch of variables y I correspond to one conic bundle structures on XD. Yes. Okay, sorry, I forgot to mention, like this question that I posed about these projectivized tangents in general. This is like very widely open. Like I asked some experts that work in Hausen in Mori Dream Spaces. Like there is just one result that I know. So if you take like a G-horospherical variety, then the projectivized tangent is a Mori Dream space, but it was proved by Fu and Liu, but they did not determine the generators.
There's no like negative examples known. I would expect this to be false in the broadest generality, but
I asked people, nobody knows. I care about Thanos, and yeah, so okay, I should maybe look what I on my notes to not just control myself what I'm supposed to say. Okay, yeah, so there is this conjecture. I really would like this to be theorem, but not yet. So, but I have some evidence that point towards that, make me optimistic that this is the case.
I mean, your example before, there was like an ideal, wasn't there? Mounting out by.
Yes, of course. Sorry. Yes.
Okay.
There are relations. Sorry,
Yeah.
I just forget about them because I certainly won't be able to determine these relations so easily. Like determine the relations is hard stuff.
Expectation in general, no.
I mean, for general Mori Dream Spaces. Yeah, I think so because like you take maybe something general type and it doesn't work. But for Thanos, this is quite interesting, and maybe for Del Pezzos it really is the case. Maybe this conjecture really is true. Okay, so
Maybe I understand something wrong, but is it maybe with the Toro's actions it should be more approachable, even
So that's the thing, that when you go to the Pezzo of degree 5, you lose any transaction. Like that's the finite group acting on it. So we cannot use any of these things that any of the tools that we have, that we know for study of these guys. Okay, so two theorems about cones. So this is this evidence that we already have. So the first theorem says that the for T x D, where D at least 2, unfortunately does not work so easily for degree 1, the Neff cone is rational polyhedral. Generated by semi-ample classes. And I can even list them. So the rays that generate the Neff cone are the pullbacks of rays of Neff XD, so Del Pezzo itself, right? And I add, interestingly enough, I add just one more ray. So ray corresponding to TXD twisted by the anti-canonical downstairs of Del Pezzo. Okay, this is a theorem. This is proved. And how do you prove this? So how much time do I have? I started at 12 past, or but when did I start? Okay, person is not there, so I just skip it. How do you prove this? We have all these nice dualities between cones. So the dual of the Neff cone is the cone of curves. So I have a natural, I list a bunch of curves, which in this case, okay, so let us consider a cone sigma, which is the subcone of cone of curves of my variety of interest. And sigma is generated by fiber of, I did not introduce P, so P is like the natural projection from my trefoil onto the Pezzo surface, and minimal lifts over -1 curves on XD. So what do I mean? I have my del Pezzo. I have a bunch of -1 curves. So if I restrict the tangent to any -1 curve, I get a ruled surface. A ruled surface always has some minimal section. So this is like a curve in this projectivization. And for every -1 curve on del Pezzo, I take a curve, corresponding curve on this projectivization. And in this way, I obtain some subcone of the cone of the effective curves. And if this is not the whole Mori cone, then when I take the dual, then I get something that is bigger than the Neff cone. But I compute the dual of this cone sigma, and it's precisely spanned by these two guys from the statement of the theorem. That is pullbacks of Neff from del Pezzo, and this one additional array. So I just need to show that this one additional guy is really Neff, and then semi-amp. And this can be done. In fact, okay, so for the grid 3, this was done by Andreas Hering, Liu, and Shao. And for the grid 2, like you can just fight a little bit with the matter, because there is like this covering from P2. So you can like work through this guy and prove that this is really semi-ample using the description of how the twisted forms, cohomology of the twisted forms looks like on P2. This was done recently by Antoine Etes. Okay, and so you get that the dual cone is really the Neff cone generated by the semi-ample class. So at least one property of being a Mori Dream space is satisfied. Okay, and the other theorem. So this is of course just a sketch, but the details are computational. So again, for P TXD D greater or equal than 2, the pseudo-effective cone is rational polyhedral. Spanned by pullbacks of -1 curves on XD. So, you know, for the del Pezzo itself, the pseudo-effective cone is precisely spanned by -1 curves. Yes, so I take the pullbacks of -1 curves. These are some effective divisors, and they are the spanning rays. And also, moreover, I take the rays that correspond to conic bundles. Okay, so this theorem says that in terms of the pseudo-effective cone, the Cox ring is, I mean, that our conjecture has something to do with the, I mean, we can believe it because the pseudo-effective cone is spanned precisely by those variables that I listed, those yi's and xi's that come from -1 curves. So, of course, there might be more generators of the Cox ring that we have no idea about, but they sit somewhere inside, and the cone is polyhedral. So both the cones that we care about are polyhedral, really. And again, the proof of this theorem is the idea is very similar. I have my candidate for the pseudo-effective cone, which is precisely what I wrote. So the variables, I mean, the pullbacks of -1 curves and these that correspond to conic bundles. I compute the dual. So this is some subcone in the cone of curves. And if for every spanning ray of this dual cone, I can find a curve in this projectivization that is smooth and that is movable, because the dual of the pseudo-effective cone is the cone of movable or mobile curves, then I'm done. I really guess that this is the pseudo-effective cone. So that's what we do. This takes more work in this case because like there is a lot of rays to check. Most of them can be like represented by some rational curves, and then you can use the existence of the contact structure to ensure that the curve is mobile really. There is also one interesting ray, maybe. So how much time do I have?
20 minutes.
20 minutes. Oh, okay. So good. So there is like a ray that for degree 5 is numerical class. So this is like how does it intersect O of 1. Okay, so so I need to like introduce some notation. So N1 P Tx D as base that consists of this O X1 pullback of the line from the Pezzo, right? Pullback of E1, pullback of E, right? This is the natural basis for the Picard group. I have some curves. For example, I have in this cone that I claim to be the cone of mobile curves, I have something that has intersection like this for degree 5. This is, of course, downstairs, this is an elliptic curve that lives in the anti-canonical linear system. But when I take like a general curve like this, then I have no chance that its minimal lift will really intersect the O of 1 by 1. So with the first coordinate, right? But if I take a specific elliptic curve that goes through these singular points of the conic bundle, then I have such a lift. Okay? Because there is one thing that I did not mention, I forgot. Maybe I should say. Okay, so when we discuss these conic bundles and these relative tangent bundle structure, so you might recall that if I have a vector bundle and I have some surjection onto a line bundle, then this gives me a section of the projectivization. Okay? And I don't have, the tangent bundle does map onto something, but this is not a line bundle, right? This is a line bundle twisted by the ideal sheet. But it's almost like a line bundle, so what I get is almost like a section. So this thing, this surjection gives me these divisors yi in P, T, X, D, and these divisors are precisely the blow-ups in gamma of my del Pezzo. Yes, so I have my del Pezzo, it has this conic bundle structure, and I have some singular points, singular points of fibers, and this yi that lives above is precisely isomorphic to the blow-up of this del Pezzo as these singular points. So maybe this is a weak del Pezzo, maybe even worse, but I have guys like this. I have divisors like this in the projectivization. So although, so I have this curve and it lifts to some curve that has desired intersections. Okay, for degree 4, I have a similar stuff, but it has 0 on the first coordinate. And then for degree 3, I have -1. What does it mean? It means, this 0 means that I have a mobile curve that intersects trivially the tautological class. So it means that the tautological class is on the boundary of the pseudo-effective cone. Then I have, for degree 3, I have -1 on the first coordinate. So it means that I have a mobile curve that intersects tautological negatively, tautological lives outside of the pseudo-effective cone. And this is very good. This is what was proved by Andreas Hering, Liu, and Shao. They proved that for their Pezzo surfaces, the tautological is big if the degree is 5 or higher, pseudo-effective but not big if the degree is 4, and not even pseudo-effective if the degree is 3 or smaller. So this is very consistent with what we obtained, right? That really this tautological is either inside the cone or on the boundary of the cone or outside of the cone. Yes. So, okay, and also, so this, okay, no, I will not mention this. Okay, so why this problem is really interesting to me is because people have been studying for Fano varieties the positivity of the tangent bundle. Yes, so we have starting with Mori. Yes, this is we all come from this. Then we have Campana-Paternal conjecture. It says, okay, which is open and says that tangent bundle is nef if and only if the Fano is rational homogeneous. This is open. These people were studying it, and people are since last 5 years have started studying bigness. So what it means for a tangent bundle to be big, and this is this important result of Hering, Liu, and Shao that I mentioned all the time. So all these results ask where does the tautological class sit? Does it sit inside the nef cone, on the boundary, in the big cone outside? And the project that we initiated is asking about how do the cones look like? Are they rational polyhedral or not? Yeah, and I guess I will stop here.